So, welcome to SHAC's first online seminar of 2023. I'm Frank James, I'm chair of SHAC, and this is a seminar series we instituted at the beginning of the pandemic, which we've decided to be so successful and useful that we're continuing the series as even though we're sort of more or less out of the pandemic. This is being broadcast live on two channels, the Zoom channel and YouTube. If the talk will last, Eric will talk for sort of 20-30 minutes, and then we'll have 30 minutes of moderated discussion. If you are on Zoom, put your hand up and I'll ask you to ask your question point personally. If you're on YouTube, I'm afraid we can't do that. So if you could just put it in the chat box on YouTube, that will be passed to me and I'll ask the question on your behalf. Now, could everybody, apart from the speaker, that is, go to mute? Otherwise, Rob will mute you externally. This month, it gives me great pleasure this month to introduce Prof Scerri, whom I've known for an awfully long time. He was educated in Britain before going to the United States in the mid-1990s, first to the California Institute of Technology, and he's now been at UCLA in the department where he, for the last 22 years or so, where he teaches general chemistry and courses in history and philosophy of science. He's one of the founders of the philosophy of chemistry. I have to say, a subject that didn't really exist when I was a student. And he's one of the and he's the founding editor of the Springer Journal, Foundations of Chemistry, which is celebrating its 25th year of publication, which is no mean achievement by any stretch of the imagination. As you can see from his opening page, Eric has been incredibly productive. So perhaps pick out one or two. Let's think mostly on the periodic table, story and significance. He wrote the very short introduction to periodic table, which is a sort of very interesting series. You only allow 35,000 words. OUP cut you at the 35,000 first word. There's a very odd length to write to, but it's quite fun to do so, and it's extremely well publicized. And more recently he's been writing about seven elements and 7 scientists. And if you want to find out more about Eric's work, he has his own website, which is ericscerri, all one word, .com. And today he is talking to us, giving us a talk entitled A Brief Philosophical History of the Periodic Table. Eric.
Thank you very much, Frank, for your kind introduction. I'll speak for about 30 minutes, if I may. So let me get straight down to business, because I'm used to speaking for more like 50, and I've had a job cutting this down. To begin by stating the obvious, the periodic table is, of course, the paradigm of chemistry, the framework, the organizing principle. There's a popular view among the general public and even among historians and philosophers of science that whereas physics and biology have big ideas, such as quantum mechanics, relativity theory, Darwin's theory of evolution, the popular and mistaken view, to my mind, is that chemistry does not have any big ideas. Now, all the chemists here know very well that that is a mistake, because chemistry has at least 2 big ideas, the periodic table and chemical bonding, and of course they are intimately connected. As Frank kindly pointed out, since the mid-1990s, there has now developed something of a philosophy of chemistry. We have a journal, we hold conferences, and there is interest in the subject matter, even though, in the popular imagination, there still is no philosophy of chemistry. Now, again, at the risk of insulting the audience's intelligence, let me ask a fairly obvious question philosophers like to ask seemingly obvious questions. What is chemical periodicity? Well, we begin by arranging the elements in a line. I've used atomic number here to order the elements. And as we walk along that line, every now and then there's an approximate repetition in the properties of the elements. So for example, the famous example of lithium, sodium, and potassium. To convert this one-dimensional sequence into a table, one takes a pair of scissors and one snips after helium, after neon, after argon, and we simply paste one strip of paper underneath the other one in this fashion. You'll notice I stop at manganese, number 25, and then I ask the question, iron, question mark. Right, we can't place iron in that position because iron is very unlike lithium, sodium, and potassium. What did the discoverers of the periodic system do? By the way, you'll notice I've omitted the noble gases. The noble gases were not known at the time of the discovery of the periodic system. Well, what the founders of the periodic system did, for instance, Mendeleev in his 1871 table, he excludes iron into this rather odd group 8, and he excludes cobalt and he excludes nickel. And after that, everything's okay again because copper does show a valence of 1. Zinc, of course, has a valence of 2 and so forth. And then you move along and then you come to ruthenium, rhodium, and palladium. And again, these are excluded from the main body of the table. And then once more with osmium, iridium, and platinum. These days, we don't do that. We don't exclude those elements. They are members or the top member of their own groups. Here they are, the iron group, the cobalt group, the nickel group. However, in the well-known 18-column periodic table, we make another exclusion of as many as 28 elements, or even 30, depending on which particular table you look at. Now, of course, it's understood that this F block shown in yellow is supposed to fit between, you see here, the 56 and the 71 that I've highlighted, and the 88 and the 103. Right? It's supposed to fit in there. But if it's supposed to fit in, why not put it in there? And some textbooks are now beginning to present this form of the periodic table, the 32-column table, which, I put it to you, is more correct because all the elements are unified together. Every element appears in sequential order. And of course, this excluded 28 elements. I mean, some of those are extremely important, more and more so technologically now, the top row being the rare earths, or some of the rare earths. Okay, the promised brief history of the periodic table with a sort of philosophical slant. Let me begin with Dalton, his famous, or one of his tables of atomic weights. This comes from his 1808 book. Once atomic weights became available, many people tried to make sense of these atomic weights and to see if there was any relationship between these atomic weights. There were two, we can say, philosophical ideas that preceded the periodic table, namely triads and Prout's hypothesis. Let me spend a moment on these two ideas. Döbereiner discovered that there are groups of 3 elements whereby one of them is the average of the 2 flanking elements in 2 respects. It has the average atomic weight, at least approximately so, and it has the average or intermediate reactivity. And this is one of the classic examples. Now, it's significant that there's this mathematical or numerical connection between them. This was perhaps the first time where there was a numerical relationship between distinct elements. And I put it to you that this is really the discovery of chemical periodicity, as I hope to explain further in a moment. Of course, it's not being spelled out yet. Döbereiner discovered other triads, as you can see here. The relationship is approximate, as you can see from the comparison of the mean with the actual atomic weight of, let's say, bromine. There was a decline in interest in triads because they were too approximate, and to many people, they appeared too much like numerology. Many people got very carried away with triads and found triads where they really didn't exist and so on. Back to that table. Now, these days, of course, the elements are ordered according to atomic number. If we consider the atomic number of these triads, the relationship becomes exact, not approximate. And it can't be otherwise because we're now dealing with numbers of protons. So take the chlorine triad, for instance, 17 plus 53 is 70, divided by 2, you get 35. In a sense, triads have made a comeback, to use a term made famous by the philosopher of science, Imre Lakatos. In fact, Imre Lakatos used this as an example of a concept that had made a comeback after it appeared to have been refuted. Here are, as we would say in the state, a bunch of triads all over the periodic table, right? Shown by these colored strips. And presumably they will eventually, if we can get there ever, they will even involve the F block elements. The second main idea that preceded the periodic table is Prout's hypothesis. Here is Prout. He was a Scottish physician working in London who looked at a set of atomic weights and noticed something fairly obvious. With the exception of a few elements highlighted in yellow, most of the elements have an atomic weight which is an integral multiple of that of hydrogen. So he made the obvious suggestion, perhaps the elements are literally composites of hydrogen, made up of hydrogen. To someone like Karl Popper, this is nice because it's a hypothesis which can be refuted. In fact, it was refuted by the careful experiments of people like Berzelius and Stas. And yet, it too has made a comeback. And it's made a comeback in the obvious sense, although modified sense, right? It's not the original hypothesis, but all the atoms are composites of hydrogen in the sense of protons, which is, and another sense is the astrophysical sense. The elements we're told by astrophysicists were literally formed from hydrogen fusion reactions. So both of these concepts, interestingly, were proposed, were refuted, and have kind of made a comeback. Mendeleev disliked both of these ideas. At least that's what he said. He disapproved of Prout's hypothesis because it smacked of the unity of matter. And he disliked that. For him, this was a form of mysticism to assume that all matter was one. To Mendeleev, the elements were strictly distinct individuals. He also claimed that he didn't like triads and that they had misled early pioneers. Well, it's true they had misled a number of early pioneers. However, Mendeleev used triads. In fact, he used triads with a vengeance. He used triads vertically and horizontally, and he published images such as this one. If you want to find the atomic weight of selenium, you add the atomic weight of the 4 flanking elements, and you divide by 4. In this case, you get 79. And the known value at the time was 78. So it's a successful method. It's using triads. Now, of course, Mendeleev was known to have been very scientifically conservative, one might say. He rejected atomic theory. There are many passages in which he outright says, I don't believe in atoms. He even preferred to use the term elemental weight rather than atomic weight in order to distance himself from atomic theory. Didn't like valence theory when it was first introduced, didn't believe in the electron when it was first discovered, not believe in the reality of radioactivity when first discovered. Noble gases, well, he eventually came round, but at the beginning he didn't. And famously, he had a dispute with Arrhenius over electrolytic dissociation. And yet, on the periodic table, he was all for it, and he is correctly regarded as the leading discoverer of the periodic table. Moving on, in this very rapid history, the Karlsruhe Conference was, of course, extremely important because atomic weights were standardized, mainly by Cannizzaro. And this pretty much opened the door for the discovery of the periodic system. As I see it, and as many others see it, this is a case of multiple discovery. As many as 6 individuals, at least, discovered chemical periodicity. The first, clearly, being the Frenchman de Champs-Courtois. Béguier de Champs-Courtois. And then Newlands, and then there's Heinrichs, and there's Odling, and last but not least is Mendeleev. Here is Champs-Courtois' famous telluric screw. in which he wraps the line of elements, the sequence of elements around a metal cylinder. And then if you look vertically, you can begin to see familiar groups like lithium, sodium, and potassium, and so forth. Newlands, from London, based in London, apparently born in the borough of Southwark in London, as was Odling, strangely enough, presented many periodic tables, spent a lot of time claiming his priority. He also reversed tellurium and iodine, something that's usually attributed just to Mendeleev. Well, here he is putting tellurium before iodine, even though tellurium is heavier than iodine. He's using numbers here, by the way. Some people have claimed that he anticipated atomic number. Well, he did no such thing, but he has, in a sense, numbered the elements rather than using their weights. Here is Heinrichs, a Dane who emigrated to the United States at an early age with this rather charming bicycle wheel periodic table. This is a good 5 years before Mendeleev. It's all there. Oxygen, sulfur, selenium, tellurium. There are the halogens somewhere here. Yes, fluorine, chlorine, bromine, and so on. Right? In some respects, he does better than what Mendeleev did. Mendeleev did not have copper, silver, and gold in his initial tables. Odling, as I said, strangely enough, also from the borough of Southwark, had a very respectable periodic table. He's the first to propose the term periodic law. He reversed tellurium and iodine. Lothar, Mendeleev's closest competitor, also reversed tellurium and iodine. And notice he has 15 groups in this table, getting on to perhaps the modern 18 groups, not far away. And the sixth and final discovery is Dmitry Mendeleev, who, as is well known, not only accommodated all the elements, but left spaces, and not just left spaces, but predicted what these elements would be like. Here are the three famous ones that were realized or discovered during his lifetime: scandium, gallium, and germanium. And then there was a fourth one with a weight of 100, which turned out to be technetium, synthesized quite a lot later in 1937 synthesized in Berkeley, but first discovered in Sicily, Italy. I've written about multiple discovery and simultaneous discovery in a book that Frank mentioned, A Tale of Seven Scientists, and I've talked about the importance of minor contributors. This is a sort of critique of Thomas Kuhn's idea that there are scientific revolutions. I believe there are few, if any, scientific revolutions, and there is really cumulative growth rather than revolutionary steps. Now, in that book, I don't talk about the discoverers of the periodic table. I talk about these seven little-known scientists: Main-Smith, a chemist; Van den Broek, the person who really proposed the concept of atomic number before Moseley; Stoner, a British physicist, discovered the third quantum number; Berry was a British chemist; Janet was a French engineer, amateur scientist, who proposed an interesting form of the periodic table that I'll come to. Nicholson was an astrophysicist, mathematical physicist, who was the first to quantize angular momentum before Bohr. Bohr got the idea from him. And Abegg, perhaps the best known of these, who had early theories of valence and attempts to explain the periodic table. Another philosophical theme having to do with the periodic table is the long-standing question concerning prediction and retrodiction, sometimes called accommodation of data. It is popularly believed that prediction, that's to say successful prediction by a scientist, is worthy of more credit than the scientist successfully accommodating already known data. For obvious reasons, it has psychological impact. It's as if the scientist knows the secrets of nature before something is actually discovered, is able to predict. But this is actually a long-standing debate. It's not quite as obvious as that. And let me give you an example from the theory of relativity. Einstein's general theory of relativity, at the time when it was first proposed, had two main tests. The first was the famous bending of starlight. Einstein rigorously predicted, that if a beam of light passes near to a massive object, it shall be deflected by 1.75 seconds of arc. Einstein, a few years later, observed the deflection during a total eclipse of the sun, found it to be 1.98 seconds of arc, plus or minus, and Einstein literally became famous overnight. There were articles in the Times of London in the New York Times. This was a dramatic prediction. But the second test was the excess precession of the advance of the perihelion of Mercury. Newton's theory could account for most of this, but there remained a gap, if you like, of 43 or so seconds of arc per century. This has been measured several times. Einstein's general theory of relativity predicts, you notice I put predicts in inverted commas because I really mean retrodicts. This is an already known experimental piece of evidence. He retrodicts 42.9, an amazing feat. Now, according to historians of physics like Stephen Brush, this feat was taken more seriously as an indication that Einstein was on the right track than was the dramatic prediction. So let me come to the elements. What about Mendeleev? I've mentioned his famous 4 predictions, which all came out right. But if we look at all his predictions, there were a total of 16 of them. Only 50% of them came out correctly. So if we're going to attach importance to prediction, maybe we should look at all predictions. And a 50% success rate, I put it to you, is not that dramatic. It's of astrological standards. Now, back to the timeline. In 1894, the first of the noble gases, argon, was discovered, and this caused problems for the periodic table. It caused problems because argon had an atomic weight of 40, which meant there was no place for it. Because if you look on my diagram below, I've shown it with an asterisk, there was already an element with atomic number 40, atomic weight 40, that's calcium. So what are you going to do with a new element that comes along with the same atomic weight? There were many other problems, whether it was diatomic or monoatomic. And there was an even bigger problem, which was that it seemed to be completely unreactive. And it remains so to this day, by the way. And so some people said, well, it doesn't even belong in the periodic table. Problems got even worse when helium, neon, and krypton and xenon were added to these completely unpredicted elements. Nobody knew what to do with them for a while. It took about 5 years. And then, so for a while, the problems had deepened for the periodic system because now the periodic system didn't seem to be able to accommodate 4 or 5 elements. The problem was, of course, solved by Ramsey himself at Frank's institution, University College. And here he is in a cartoon from Punch magazine pointing to the new group which he created, the noble gases, at the right-hand edge of the periodic table. What is not well known is that one or two people had predicted the noble gases. And for instance, the Danish chemist Julius Thomson, back in 1895, predicted that there should be some new elements with the following atomic weights: 4, 20, 36, 84, and so on. Now, take a look at this. It turns out that there were such elements. They are helium, neon, argon, krypton, xenon, radon, and oganesson. And the average